Welcome, ladies and gentlemen. On behalf of the Mexican Water Society and Tecnológico de Monterrey, we would like to introduce our expansion project for Pflugerville Central Wastewater Treatment Plant. The members of this team are Adriano Suberza Carrano, María Fernanda Aedo Segovia, Inés Rebeca Morillo Serrano, and Brian Eduardo Rodríguez Ávila.
This project has been divided into 4 main topics: the project analysis, the design calculation, the decision-making process, and the design proposal. In this presentation, we are going to explain the research made by the team in order to provide the results needed for the improvement of the project's design. We will display the items considered under this study, how the problem statement will be addressed, the current configuration of the wastewater treatment plant, its regulation, and the parameters that it must comply with. Also, it is important to mention that the calculation behind this design can be found in the appendix of our written report. For the implementation of this project, we sized the missing facilities and took into account for the flow diagrams both the existing and the proposed equipment. Once we had this information, we developed several alternatives to tackle all the issues troubling this plant in order to improve its efficiency. Finally, we form a decision matrix to visualize the advantages, disadvantages, and the cost of each alternative, and we illustrate the final alternative in detail through a flow diagram and a construction timeline.
The wastewater treatment plant is located in the city of Pflugerville, a city that has had an incredible socioeconomic growth in recent years. In 2014, the city of Pflugerville also had in its inventory another wastewater treatment plant named Wilk Lane, but unfortunately, this plant was shut down. In 2016, the plant reached 75% of its design capacity. In 2017, the city of Pflugerville won for a 4th time a recognition as America's best place to live. With this being said, it is necessary to redesign and upgrade the plant. These improvements are fundamental in order to sustain the future population of the city of Pflugerville. By implementing these upgrades, the city will avoid problems related to environmental management and public health. Furthermore, it will avoid the loss of industry, the decrease in employment opportunities, and pure water services infrastructure. Finally, by improving this plant's design, its current environmental, social, and economic conditions will not be put at risk.
As the main objectives of this project, we have to increase the flow capacity, maintain the quality of the effluent based on the regulatory standards of the area, as well as guaranteeing good quality water to maintain the suitable growth of the future population.
Now let's look into the flow diagram of the plant's existing configuration. On this diagram, we have the primary treatment, which consists of 2 screw pumps and 2 automatic fine screens, which allow the removal of large solid waste at the entrance of the plant. From there, the flow reaches a splitter box that divides it into 2 aeration basins with their respective mechanical aerators. By following the diagram, we arrive at a second splitter box, which divides the flow towards the secondary treatment. This consists of 2 secondary clarifiers with 2 sludge outlets and 1 water outlet. The first sludge outlet goes to a centrifugal pump, sending 1 fraction of the sludge to disposal, and the second one returns another fraction of the sludge to the primary treatment. As for the water outlet, it reaches 2 chlorine contact basins connected in series, which work with chlorine as a gas. For the tertiary treatment plant, we have 3 basins with disc filters and a post-aeration basin. Finally, the treated water reaches a partial unit that exits the flow as the final effluent. In this slide, we are comparing the plant's current design parameters with the plant's ideal design parameters. On the left, we can clearly see that the average flow and peak flow for the current configuration are 5.3 and 17.4 megagallons per day respectively. We expect that this final configuration will allow us to satisfy the future water demand while meeting the quality parameters. In order to achieve this, we intend to double the treatment capacity of the plant to 10 and 35 megagallons per day respectively. The table on the left shows the average current concentrations plus 1 standard deviation for the influent. These parameters were the basis of our calculations as an inlet quality reference to decide the appropriate treatment units for all the alternatives. The table on the right, which represents our target in terms of effluent quality, identifies the monthly average discharge limits for the same parameters. these concentration limits that monitor the biological oxygen, total suspended solids, nitrogen, total phosphorus, E. coli, and dissolved oxygen are the ones we intend to reach with our final treatment design.
As for the methodology to alternatives, which are 5, there are similarities in some processes, such as the preliminary treatment, which consists of screens, a grid removal system, and primary clarifiers, being the only difference the type of screens or the number of units in the grid removal system. The units that are distinctive in each alternative will be mentioned, as well as some advantages and disadvantages of that configuration. For the first alternative, we are going to accentuate the type of disinfectant, which is sodium hypochlorite, as well as the presence of the existing centrifuges for the sludge management. The benefits that this alternative provides are it allows the handling of large volumes of flow, offers optimal protection for downstream equipment due to the grinder set at the entrance, and it comes with a robust primary treatment. However, the hindrance it presents is that both submersible pumps and centrifuges are sensitive equipment and tend to clog easily. The cost of this configuration is nearly $7,600,000.
The distinctive thing about this second alternative compared to the previous one is that instead of the combined configuration of submersible pumps and grinders, this one remains with the existing screw pumps. The alternative contemplates quartz screens instead of fine screens, and additionally, instead of sodium hypochlorite, the use of chlorine gas is proposed for disinfection. Disadvantages of this alternative are that screw pumps do not imply an additional cost. Chlorine gas contact basins are inexpensive and there is no need to train maintenance personnel because this equipment is already familiar to them. And band filters facilitate sludge management maintenance in contrast of the centrifuge previously mentioned. On the other hand, the disadvantages of this equipment are the potential risk in the disinfection unit due to the flammable properties of the chlorine gas, as well as high costs due to the need to construct several units and large space requirements. The cost of this second alternative is around $6 million.
The differences that highlight this configuration are the implementation of submersible pumps, fine screens, and one vortex sand trap, which are capable to withstand the peak flow. Some of the advantages are the operation ease due to a reduction in the number of equipment in the same process like in the grid removal system, and a higher efficiency in solids removal due to fine screens implementation. Two inconveniences of this configuration are the high cost due to velocity controllers of the pumps and an increase in frequency maintenance due to sensitive equipment.
For the alternative 4, we left the original screw pumps and we added the MBR technology in the secondary treatment. These membranes are placed inside a second clarifier in order to treat the 2-hour peak flow. Another difference is the direct connection from this tank into the partial unit to exit as final effluent. As for the average flow, we chose sodium hypochlorite as a substitute for chlorine gas due to security reasons and left the original number of disc filters that the plant already had. Some of the advantages of this alternative are better water quality in the final effluent thanks to the addition of MBR technology, as well as the absence of disinfection and filtration units for the flow fraction treated by this technology. As for the disadvantages, we have an evident high initial investment and the lack of enough customers to justify such good quality in the final effluent.
We will show to you the flow diagram in stages to visualize the trajectory of the water train as well as the sludge train. For the primary treatment, the proposal counts with the 2 existing screw pumps, 4 mechanical fine screens, 2 existing plus 2 additional, 2 vortex sand trap proposed, the addition of EcoSorb prior to the primary clarifiers in which alum is added as function of chemical enhanced precipitation treatment, and a splitter box to distribute the flow entering the aeration basins.
In the secondary treatment part, an IFAS, which for its acronym in English is Integrated Fixed Film Activated Sludge, will be added to increase the capacity of the reactor without the need to construct an additional facility. Moreover, this technology helps in the removal of nitrogen. Also, 3 contact basins will be added using sodium hypochlorite as a disinfectant.
The tertiary treatment was maintained with the same existing technology of the original plant design, only the amount of equipment had to be doubled to meet the target demand. Finally, after tertiary treatment, at partial flume device the level is gauged. The outstanding advantages of the final proposal is the ease of operational management thanks to the design of 2 independent water trains. It guarantees a low or almost nil odor emissions, high energy efficiency due to the presence of turbo blowers and high removal of nutrients, mainly phosphorus and nitrogen as ammonia. While the only prominent disadvantage is the dependence on a significant amount of chemical consumables, leading to an approximate cost of $6.7 million.
With the proposed configuration, an estimate of the parameters was made in the effluent. For both biological demand for oxygen and total suspended solids, the limit of the standard is 5 mg per liter, and our estimates are 2.36 and 3 mg per liter, respectively. As for nitrogen in the form of ammonia, the standard is very strict with a limit of 2 mg per liter due to the threat of toxicity in water receptor bodies, as well as the need to control eutrophication or algae proliferation. Because IFAS had limited application, its design criteria are still evolving, and the knowledge of the process is growing through pilot studies, which conclude that with an average range of 25 to 40 mg per liter of ammonia in the influent, a range between 2 to 5 mg per liter of ammonia can be reached in the effluent. For total phosphorus, the standard calls for 1 mg per liter, and with an efficiency of 90% relative to the influent, our estimate is 0.79 mg per liter. In E. coli, unfortunately, the input value is not available, but by properly performing the disinfection process, this aspect removal efficiency reaches 99% so that the standard can be met. And finally, for dissolved oxygen and by the post-aeration process, a minimum of 6 mg per liter can be warranted at the output.
As you can see, the cost of the alternative 5 is the second lowest and yet is the most equipped one. It is important to mention that the cost of these alternatives only contemplate the additional equipment and units, do not consider maintenance costs, chemical costs, and energetic costs, which were all taken into account for this project and are included in the written report. All costs are quoted in US dollars.
Construction timeline. This table of the construction timeline was generated where the division of the time in both years and months is shown in the upper part. On the left side, we divide the remodeling project in 3 stages: project analysis, construction drawings, and by the last stage of the construction process. For the first stage, which is the analysis of the project, we have in the description the background information, the statement of design, the preliminary works, the information analysis, and the alternative analysis. For this first process, we propose a duration of 6 months. Now, for the second stage that corresponds to the construction drawings, we have the drawing for the primary, secondary, and tertiary treatment, as well as the design of the general plan, the structural distribution, and the design of the effluent. For this stage, an estimated time of another 6 months was proposed. For the third and last stage, which corresponds to the construction of the preliminary treatment, the primary treatment, the biological and chemical process, the secondary and tertiary treatment, the design of the effluent structure, and finally the sludge treatment, where a time of 8 months was estimated for the entire construction process. Equally, these tables shows the processes that overlap. This is because in some cases it is possible to work with different concepts at the same time to reduce the work time.
After the completion of this project and as final conclusions, we can firmly say that we successfully met all quality parameters and future flow demand. We made full and total use of the plant's current technologies and operational units. We considered all impacts to operation and maintenance requirements and costs. We improved the safety, and operational simplicity to achieve an adequate management. We reduced costs as we made a special emphasis in energy consumption reduction. And finally, we considered the public health, the protection of receiving water bodies, and the reuse of water for industrial purposes as the cornerstone for a treatment design.
Additionally, our team has multiple interdisciplinary abilities within the areas of chemistry, sustainability, and civil engineering. Because of this, our team is ideal for the development of this project. Finally, last but not least, we want to give a special thanks to Dr. Roberto Gallo, Dr. Hector Barrios, and Engineer Saúl Garcia for their mentoring and support during the preparation of the project. We also want to acknowledge and thank the companies Cromo Industrial Monterrey, Reminsa, Galler, Ecosor, Grupo Nergua, and Agua y Drenaje de Monterrey for their support in equipment specifications and quotes.